Okay, we are pleased to have Kajal among us to give second lecture on landscape in string theory. Over to you, Kajal.
Thank you. Okay. Am I audible? So, to recap what we saw yesterday is when going from some d to d minus 1, where we were compactifying on S1 cross some manifold d minus 1, we had some moduli fields which were corresponding to the compactified metric, and we assumed at that point that to stabilize these moduli fields we'll need a potential for them which will look like some field strength square and then square root of minus g. And then also we learned about little bit of homology and cohomology, which we will use today. And we saw for a Kähler manifold, I will define what Kähler manifold is today. The homology class can be decomposed into following form. So HK can be written as P plus Q equal to K H P comma Q, where P were correspondent to holomorphic components of a P comma Q forms, and this were corresponding to the anti-holomorphic. And we also said that the dimension of this cohomology class is given by something called Hodge numbers, which were H, P comma Q, and yeah. Okay. So, sorry. Now, we know what a real manifold looks like, what a real manifold is, and generally we can take a real manifold, a 2n dimensional real manifold, and we can define coordinates on that x. Let's say we have coordinates on the real manifold to be xi and yi. This is n and this is n. Then we can define some complex coordinates zi, which can be written as xi plus iyyi. Now, once you have defined this complex coordinates on a real manifold, we can define a tensor. So, on a 2n dimensional real manifold, we can define a tensor J, which looks like this: dzi cross del del zi minus I dz bar I bar and del del z, where these are kind of basis of tangent and cotangent spaces. And Z can be written, the components of Z can be written in this complex coordinate to be I times minus I identity and J square to be minus 1. Okay. Yes, sorry. Yeah, thank you. Now, if we have a real manifold where we can define such a tensor, what we call that manifold is almost complex manifold, and the J is called almost complex structure. Now, from going from a real manifold to complex manifold, J has to satisfy more conditions, which I will not talk about, but extra condition after imposing some integrability conditions on J. So, if so any 2n dimensional real manifold where we can write such a tensor, that is called almost complex manifold, and J is called almost complex structure. So this is now if J satisfies some extra integrability conditions. Sorry? Yeah. So, okay. I think the sign is for like overall this J to be, you know, real tensor basically. So when you substitute Z and Z bar to be this X plus Iy and X minus Iy, then what you will get is a real tensor.
From here, the matrix form, this is purely imaginary.
Yeah, it's in the complex coordinate. When you write it in real coordinate, J will be like in real coordinate. Okay. So and this is required because in complex manifold, let's say you have two different patches. So to go from one patch to another patch, you have to have a holomorphic transition function, and for that J had to satisfy some integrability condition, and once J satisfies that, then the resulting manifold is a complex manifold. And now J is called complex structure. Okay. Now after that we can define a metric on manifold. So a Hermitian metric is defined as follows: for any two vectors u, v and w, if g of v and w is same as g of j transformed v and w, then G is called, or G is Hermitian metric. Yes. Yes. Yes.
You are doing this redefinition of coordinates. Why do you need to impose additional constraint like for J?
So
Like, is it a new constraint?
So not all complex manifold, I think, can be expressed in terms of 2n-dimensional real manifold.
Other way around. Not all 2n-dimensional
Oh,
real
oh.
manifolds are complex manifolds.
Yeah, yeah.
Like,
Sorry.
let's say you decompose this into Z and Z bar in some chart. Okay. Now what you're essentially saying is that there is some holomorphic direction, anti-holomorphic direction. Now if I go to a different chart, if it's 2n real dimensional, it's a smooth map. But under smooth map, Z and Z bar can mix. The only way Z and Z bar can't mix is if it's holomorphic. So holomorphic is an even stronger restriction than smooth maps. So if you want complex manifold, you want something stronger than smooth transition functions, you need holomorphic transition functions. So even though all 2n-dimensional manifold, you can always write some tensor that looks like it's complex. For it to be actually complex, you need this split between holomorphic and anti-holomorphic transition. And that requires some condition on this J, some commutator, something.
Yeah. Okay. Now we can write a metric on a complex manifold as Gi J bar d z dz bar J bar, where these are only holomorphic functions. So Gi J bar are only function of Z. Okay. And these are Hermitian because taking the complex conjugate, Di J bar is same as Gi bar J. So, okay. So, given any Hermitian metric, we can associate. So, these are all definitions. 1, 1 form omega, which can be written as Gij bar dzi which dz bar. Okay. Now, why we are kind of introducing this 1, 1 form? It is because we want to define a volume on this manifold. So let's say we have n-dimensional complex manifold. Then omega to the power n, which is basically in wedge product notation, will be omega n times, and this is equal to minus I to the power n determinant of Gij bar dxi wedge up to dx 2n. So I have kind of written the complex coordinates in terms of real one. So and this I to the power n determinant of Gij bar is basically equal to some determinant of G mu nu on this in x coordinate. So you know that, I mean, yeah. So this is how the volume is defined. And now if I impose one more condition on this omega, that is this omega is closed, then the resulting manifold is what we called scalar manifold. Okay, because once you impose this condition, you can basically write your metric as some derivative of scalar function. So k, where k is called basically scalar potential. Okay. Now we have all the elements to define what a Calabi metric is, But before doing that, we need to understand why we are kind of compactifying on Calabi-Yau metric. And there are two main reasons why we want to compactify on Calabi-Yau metric. So let me just list those. Oh yeah, so, yeah, right. I forgot the combination of these boards. So the first thing we want after compactification is that our four-dimensional manifold should look like something like Minkowski. And for that, what we need is the vacuum solution of 10D theory to have a structure of this M4 cross X6. And the second thing which we want in our four-dimensional theory is supersymmetry. So in four-dimensional theory, we want some preserved supersymmetry. And that basically translates to having a manifold which is Ricci flat. So we have R small m comma n equal to 0, where m and n kind of go from 1 to 6 for compactified manifold.
Why do you want the 4D
That is how, the observations are telling us, like our world is kind of Minkowski asymptotically. So we want the vacuum solution to look like this, and the X6 should be compactified, right? Yeah, it's the background metric kind of. You can have fluctuations around it.
In terms of two derivatives of the Kajal potential, that's a local statement or that's
I think it is global.
you can write it like that.
Scalar potential, yeah. Do you have any concern?
I thought if it's globally defined, like even the Kajal form also can be written as some derivative of Kajal potential, right?
Yes.
So if that is globally true, then from Stokes theorem, that form has to just be 0. Like top form can never be D of something, right?
But that is not top form, right?
The Kajal form, the top. I meant the omega.
Omega, okay, holomorphic.
No, I'm saying omega to the n.
Okay, right. Oh, then maybe it is local, sorry. Yeah.
So when you reduce it, you take a genetic, you take a 10D and then you reduce the action on that, right?
Yeah.
So why you talk about a particular solution in 10D theory?
Because the kind of vacuum of the 10D theory is our 4D theory, right? You took a solution around some vacuum values of 10D fields, and then integrate out this, higher dimensional fields, and the resulting theory is our effective 4D theory.
But where was vacuum in your yesterday's discussion?
So, okay. Let me just recall.
I thought you wrote some genetic answers for GML and then you reduced your action based on that.
Yeah, I mean that was just a toy model. So, I mean generally you can write your metric to be some G capital MN, and then it is G mu and
So you were saying that you are assuming something for this.
some kind of, yeah, and that is basically set to eta mu, and when you talk about, you take the fluctuations around it, so that is why.
I thought you would keep that G mu generic, and you reduce, you come down to a lower dimensional theory, then you solve your Einstein equation or whatever to get your vacuum in the lower dimensional theory. I mean, we don't reduce over a particular solution, we reduce over a generic solution, and then we come. The action is has all possible solutions.
Yeah, but not all solution will have the isometries of 4D, right? We want the Poincare invariance in 4D. For that, we need to kind of fix this G mu to eta mu, and this is only possible solution we have. Only extra solution we can have is some kind of y dependent, which is why I'm calling the the coordinates on this manifold. So you can have some e to the power a y kind of thing sitting here. So G mu has to be fixed around this eta mu, the background.
But then for your lower dimension theory, the action is for a particular solution. It's not a. So when you get your 4-dimensional action,
Yes.
that is some on-shell action for some particular solution.
Yes. Yes.
It's not a generic.
No. Once you fix the higher dimensional thing, then you will get the 4-dimensional action. So that was the problem we were having yesterday, that we had one scalar which was massless. So we wanted to fix that to some background value, and then we will have the effective theory in 4D which we want from
But
phi.
scalar doesn't come from the scalar is like this.
Is your question why we want a vacuum theory to be of that form or
No, I
something?
mean when we reduce, and when we do this reduction, we have some generic answers for the
Right, right.
Then you reduce the action over this answer.
Right.
You get some lower dimensional action. But the lower dimensional metric is completely dynamic. It can take any value unless
Right.
you improve the equation.
Right, right.
I'm saying is that when now she is reducing her technique theory, she has already chosen a particular form of the metric, which is like some.
M4, yeah.
Yeah, actually this is a requirement. These are the two requirements which you want to reproduce standard model like the models, because we want to match string theory predictions, let's say, or can string theory give you standard model like models? Okay, so in lower dimension, yeah. So here
You can always have these fluctuations, right? So eta mu is kind of like background metric you have, and around that you can have this fluctuation.
but that you can only study when your metric is dynamically lower dimension. No, but in standard model,
So-
do you worry at all about single model? I'm just asking from general. Yeah. So I think the motivation behind this is to reproduce standard model physics. Okay, so the lower dimensional action is not dynamic, off-shell, right? Yeah. So this is our requirement.
Lower dimension you have this modes H mu, which will give you value.
Yeah.
So to begin with, in the higher dimensional theory, you are expanding the fields around some vacuum and then reducing the fluctuation.
So my answer is eta mu plus h mu based on which I'm reducing. Or is it exactly eta mu?
I mean, we are kind of reducing only on eta mu, but then they can have fluctuation which are in h mu, and then you'll have the So the vacuum solution will be around this.
No, this is fine. This
Yeah.
is fine.
So that will give the 4D standard model.
You can still give me some dynamics in lower dimension.
Yes. Yeah.
So these compact and X6, the compact part of the manifold, that you want to be Ricci
Yes.
and in the definition of the Kajal manifold, it was not like, was it anywhere said that it was compact?
I think to define this, you need to be have a compact manifold. So the Kajal.
No, I think isn't C all C M of scalar? Isn't it? Like C1 is scalar, right? The usual complex plane is a scalar
Yes,
That is not
but
compact, right?
that is
I think
Mm.
if you allow for compact, not all dimensions will, like S2 is scalar. I think S4 is not scalar or something like that. Like there's some dimension depending.
I don't know exactly. Okay, I don't know exactly, so, but
At least for the non-compact one, we can use C as the example. Right? Like one
yeah,
example
yeah,
we
yeah,
have is
yeah, yeah.
non-compact.
Okay, so these two property, and so we define our Calabi manifold. So a Calabi threefold I am calling, because we are kind of compactifying on 6 real dimension or 3 complex dimension, is a compact scalar manifold with SU3 holonomy. Now this SU3 holonomy will imply some conditions on the Hodge numbers. So first of all, H0, 3 is 1 and H0, P is 0 for P less than n and greater than 0. Okay. So the SU3 holonomy is kind of a condition that comes from demanding that we have a covariantly constant spinner on the manifold, and that because on 6 you have kind of SP, this spin 6 group, and that is kind of a, you know, so on SU4, in 4 representation, you can have a spinner which looks like something like this, and for it to be covariantly constant, the transformation matrix should act on only these 3 components, and that is basically what we have in SU3. So the SU3 holonomy is required to have a covariantly constant spinner on the manifold, and that is kind of related to the condition that we have a Ricci flatness of this compact manifold. Okay. Sorry.
So in the 4D theory, we want some SUSY, and that somehow translates to the Ricci flatness of X6.
Yes.
And
We want some epsilon kind of to be 0, right? This epsilon is related to some, transformation of field under supersymmetry, and that will translate to, in higher dimension, some Rmn, gamma n, epsilon to be 0. Okay, and since the other manifold is flat, so the R mu nu is itself 0, so we need to demand that this one is 0.
And this holonomy, what did you mention?
So the holonomy kind of comes from this condition itself, that Rmn is 0, and so I don't know exactly how to get that, because the SUSY part I am not very confident about. So the only thing is that in 6th dimension you have like SO6, and then that is isomorphic to the spin 6 over Z2, and this spin 6 is a subgroup of this SU4, and in SU4 representation you can write any spinner on this as kind of 0, 0, 0, not any, but at least one you can write. And for it to be, this is a constant value setting here, so it to be covariantly constant, the transformation matrix should act on only these 3 components, and that is basically resulting in this SU3 holonomy. Okay. Yes.
Then isn't it including that H03 also? If you said P equal to 3
No, P is less than n.
and N is?
N is the dimension of this manifold, so it is 3, sorry, in our case.
What exactly is H?
H are the Hodge numbers. So yeah. So we have, so yesterday we had these conditions that H R comma S is same as H D minus R, which is now 3, and 3 minus S. And also because of the complex conjugation, we had this condition. And these two conditions combined with this one, now we have the Hodge diamond for Calabi-Yau 3. That is sorry, let me just write what are these, so I will not have any extra things. So for 3-dimensional complex manifold, we have H0, 0, then H1, 0, H0, 1, and we have H2, 0, H1, 1, H0, 2, and we have H2, 1, H1, 2, H0, 3, and H3, 0, and then we have so one more. Okay, let's just have this many right now because the lower one are kind of symmetric. So H00 is 1, and due to that condition, these two are 0, and H2, 0 is also 0, and H3, 0 is 1, and only independent ones are H1, 1, H2, 1, and H1, 2 is again same as H2, 1, and we have here H2, 2, which is same as this one. So same thing will be kind of mapped there. So only this middle part of the total Hodge diamond is what we are left with, and out of that we only have like 2 independent Hodge numbers for Calabi-Yau 3 manifold. Sorry, it's kind of connectedness you define on the manifold, right? So H0 was like taking the, only the points, some coordinate you are defining. So oh, we will see. So we need to classify this. I mean, yeah, let's see. Okay. So now I will talk about moduli space of Calabi-Yau manifold. CY3. So the parameter space of this any manifold, or at least Calabi-Yau manifold, is kind of given by this condition that Rmn of some metric G is 0. Now one can ask how many different variation we can have of this G such that given this Rmn G plus del G is also 0. Now the obvious answer to that is that this G and this new G, so G prime and G, are related by some coordinate transformation, but we are not talking about these. So we need to fix a condition such that we kind of eliminate all G's which are related by coordinate transformation, and the leftover components of G will be kind of our moduli fields. So to fix that, we need to impose this condition that del mu of delta G mu nu is 0, and that is equivalent to eliminating all G primes related to G by some transformation. So I am writing it xm plus xm going to xm plus some psi m. Okay. Okay. So now what we can do is expand this condition in linear of this variation delta G, and that will look like something del rho, or in this case del m delta of G n p plus twice of R n some m p and R delta of G m R. So we have just expanded this equation star up to linear terms in the variation of the metric. Yes.
Can you just
Yeah, yes, sure. Okay. So why I defined these kind of complex manifolds and Kähler manifolds, then Calabi-Yau manifold, is that we'll need those things, the omega, which is kind of the 1,1 form on the Calabi-Yau manifold, and we'll need the concept of the complex structure as well to understand how the moduli fields are kind of in the Calabi-Yau manifold. So the main aim for, this thing is to kind of understand the moduli space of the Calabi-Yau manifold. Before that was just kind of definitions and stuff. Now the Calabi-Yau, the moduli space is kind of given by all variations delta G, such that they satisfy this condition that R m n for this 3 manifold is 0, and they should not be related to each other by some coordinate transformation. Okay. Now so for that, what I am doing is kind of expanding this condition in terms of this variation, linear orders in variation, and now we will see that they kind of give us two types of moduli, what we call Kähler moduli and what we call complex structure moduli. Okay, so that's why the Kähler form and complex structure forms were kind of defined.
Was that we wanted the RMN to be 0 and the reduced manifold to be Minkowski. This will
Yes.
be only like sort of physical
Yes.
could be put. Now the thing that you're saying is that this does it necessarily imply that the X6 is always Calabi-Yau threefold with SU3 holonomy the way that you've written? Is it or is it just some?
Yeah. So for SU3 holonomy, it is always Calabi-Yau. So definition of the Calabi-Yau is this is a Kähler manifold which is compact and has a SU3 holonomy.
Okay. So the fact that it had to be Kähler was what was the requirement for demanding that it be Kähler?
So phenomenologically, the requirement is that we have minimal supersymmetry in the compactified theory. So let's say you start with n is equal to 1 supersymmetry in 10D, then you are left with only n is equal to 1 supersymmetry in 4D. But if you take like torus, which is also a compact Kähler manifold, but in that case it preserves all the supersymmetry. So n is equal to 1 in 10D will be kind of either n is equal to 4 or 8 in 4.
And
Yes.
And that is like for 4D it's SU2 cross SU2, for 6D it will probably be SU3 cross SU3, but complex will be SU3.
SU3, yeah. Yeah. Okay. So in the case when the manifold is scalar manifold, that is the metric is only having this component Gij and it is Hermitian, and we can have d omega equal to 0. One can check that this condition reduces to two different conditions. One is on del Gij bar, and the second one will be kind of on the del Gij or del I bar J bar, which are complex conjugate to each other. So when we are going from this G prime to G, what we are doing is, so let's say we have Gij, that will go to that Gij bar, some Gij bar plus del of Gij bar, and we can also have this, pure indices variations as well, but that will have to satisfy this condition. Okay, so the first one is corresponding to this mix index, and that can be written directly from that equation to be del mu, sorry, again I am writing, okay, let's write del mu delta of this Gij bar plus twice of this R I K J bar L bar and delta of Gk J bar to 0, where mu is kind of k comma k bar index, or k comma k, since we are writing them as that. And this condition implies that delta, which was the Laplacian in our case, acting on this del G form Ij bar equal to 0, it can be easily seen once you kind of substitute delta to be d plus d dagger square, and then write them in terms of this del bar things. Okay, now this looks like that the variation of the metric correspond to some 1,1 harmonic form, right? Because the Laplacian acting on this del G is 0. So let me just write. So the delta Ij bar correspond to some 1,1 harmonic form, and we have one such form which is our scalar form, which we defined in maybe second board, that was omega. So, and also we know that this delta acting on del G is kind of equivalent to saying that d of del G and d dagger of del G is 0. So from this condition, we see that it is kind of lies on the cohomology class of 1,1 forms, right? So for cohomologically non-trivial scalar form, so that means that omega plus del omega is kind of same as omega, where del omega are kind of given in terms of del G, because we wrote omega to be I times Gij bar and dz wedge dz bar with appropriate indices. Yeah. So for cohomologically non-trivial Kähler form, any Kähler form, what we get is a Ricci flat metric. So let me just rephrase what I want to say. So we started with the condition that we want the Ricci, there to be a Ricci flat metric in this Calabi-Yau manifold, or yeah, and then we wanted to see all possible variations of this metric which are not related by this coordinate transformation, and that will basically parameterize the moduli space of the Calabi-Yau manifold. And for that we had that condition, and for using these two conditions, that Gij is Hermitian and d omega is 0 for Kähler manifold, which was the definition of the Kähler manifold, we can kind of split these into two conditions. One is for the mixed indices and one is for the pure indices of the variations of the metric. I will do the pure indices. And when you do that, the mixed indices variation of the metric is kind of equivalent of saying that all these variations lie in the cohomology 1,1 class, and that is same as saying that if we have a Kähler form which is non-trivial for in cohomology class, then all these Kähler form lying in that cohomology class will give a Ricci flat metric. Is that okay?
Sorry, so can I just?
Yeah.
So what are these mu indices running
Oh,
over?
so sorry. I mean, so mu is like k comma k in this, and all others are mn.
So the condition it reduces to for these mixed indices, that is just this delta of Gij has to be same, right?
Yes.
And that tells you that del G is a 1,1 harmonic form.
Yes. That is kind of del G is 1,1 harmonic form, or can be parameterized in terms of 1,1 harmonic forms.
Through this cohomology.
Yes. Now, because these variations are kind of parameterized by this scalar form, the moduli fields corresponding to these del ij bar are called Kähler moduli. And due to the cohomology equivalence, the number of these Kähler moduli are given by the dimension of this 1,1 cohomology classes. Yes.
It was, ds square was Gij bar, dzi tensor dz bar, right?
Yes.
And now if I allow for a delta Gij variation, I'm creating a dz tensor dz kind of a.
Yes. So we will see how to get rid of, like, I mean, that is kind of like definition of why we need, I mean, why we have complex structures moduli. So okay, let me just.
So why is it related to H1,1?
Huh?
Why is this delta I? Delta
Okay, so let me just expand delta Gi in terms of the 1,1 harmonic forms. So I can write delta Gi j bar to be sum over sum alpha, which runs from 1 to t tilde alpha and b alpha ij bar, sorry, where this b ij bars are 1,1 harmonic forms And if you remember, there was a kind of equivalence between harmonic forms and the cohomology classes. So we will have only h1 comma 1 such basis vectors and tensors, and when we expand in terms of that, these kind of coefficients which are real at this point, so these are real, will basically be what we call the Kähler modeling. So T tilde alpha, alpha going from 1 to h1 comma 1 are does that answer? Okay. Okay. Now the second kind of variation we had were the pure indices variation. So delta G I bar J bar, and again we can reduce the constraint we had coming from the flatness, I mean the Ricci tensor to be 0. In this case it will be and again this is kind of equivalent to a little bit different constraint. So we are taking the Laplacian only for the anti-holomorphic exterior derivative. So it is Gi to be 0, where I'm del Gi in this case is del of Gi J bar dz bar J bar, and del Gi bar J bar is nothing but Gij K prime, and the related to the pure indices variations. Is that okay? So similar to previous case, what we can say about this is that this belongs to, I mean these variations. So delta G I bar J bar belong to H del bar 0 comma 1 cohomology classes. Now, okay. So given a metric and a complex structure form which we had J, so given a metric and a J, we can go to a coordinate where we can reduce the metric to look like this form. Okay. Now because these new variation are kind of changing the indices, what we need is a different complex structure. So some J prime G prime, and corresponding to that metric we can go to corresponding to that complex structure we can go to a coordinate where our G prime will look like Gij bar, but these two will kind of give us the same things when we now. Since for the Calabi-Yau we saw that because of the SU3 holonomy H3 comma 0 is 1, that basically means that we can have one unique 3 comma 0 holomorphic form that is omega. And by using this 3 comma 0 holomorphic form, we can kind of parameterize the space of this moduli fields corresponding to the pure indices variation in the metric. Unique up to cohomology, like
Like if I write f of z omega,
yes,
that is also h3 comma 0.
yes. I mean, yeah, up to, yeah, right, up to some function. That function, the mod of that function will be fixed by, you know, the mod of omega and metric. I mean, depending on, yeah, up to some normalization, it is unique.
So when you had G, you had a corresponding complex structure J that told you the given light metric.
Yes.
Now, this G prime that you have is not related to G by some coordinate, right?
No.
You're trying to find the ones that are not. So what guarantees that I can still have a G prime?
As long as you have a J prime, you can have a G prime which looks like this. But sorry, could you just rephrase?
So my question is that these you have some non-trivial condition for this delta G of I bar J, right?
Yes.
And the point is that if I can always write the new metric that I have after this delta G transformation as G prime of I J bar, then that means this condition should be trivially satisfied, right? I mean, for the same indices, they should focus on it.
No, I think
No.
what will happen is that, so this condition, this G prime J prime is G prime of I J bar, that's equal to saying that there exists some basis where that metric is diagonal. So you have, let's say, started a diagonal metric,
Right.
okay, then you do some variation that is not related by coordinate transformation, you will create non-diagonal terms. And then there exists some coordinate transformation where I can bring it back into diagonal again. So that is what you're saying, right? Like something
Yeah.
along those lines.
I mean, yes. So as long as you have a this complex structure, then given any indices type of metric, you can write it in terms of that. But when you do the transformation, which is not related by coordinate transformation, then you need a different complex structure to bring it back to, you know, this form. So that is kind of. Now, so using this 3,0 holomorphic form, we can kind of relate this G I bar J bar as omega I J K del G K, this is L, and dz I wedge dz J wedge. So these this is kind of a 2,1 form or 1,2 2,1 form, and the condition that this form should be closed, so this, let's say it's chi, will translate to the condition we have for this pure indices matrix, that it should satisfy the Ricci flatness condition. Okay. And again, similar to the previous case, we can kind of expand this variation in terms of this harmonic 2,1 form. So omega I J K del G K J bar can be written as sum over alpha going from 1 to H2, 1 T A, sorry, alpha B alpha I J L bar. So this is L bar, and these TAs or T alphas are called complex structure moduli. And there are H2,1 complex structure moduli in a Calabi-Yau threefold. Is that okay?
Can you repeat that again? What is chi?
Chi is this form.
Oh, the whole thing is
Yeah. So this is defined to be chi, which is a 2, 1 form. Now I'll do the example for this. Sorry. I mean, D is kind of given in terms of del del bar, so both of them have to satisfy this. So only the del bar cohomology, because for the complex, manifold, we only defined this del bar cohomology, and that was some requirement which I don't have answer to, but some requirement that we are only working with some holomorphic vector bundles or holomorphic transition functions, that kind of thing. So for that you need to have this omega bar, del bar cohomology. So it is a 2, 1 form, and okay, maybe I should not write it like that, but it is obvious that it will lie in 2, 1 cohomology because of the fact that the condition for the Ricci flatness was translating to this thing, which was delta del bar of del gi equal to 0, and omega is a 3, 0 holomorphic form which lies into the 3, 0 cohomology classes, because of the SU3 holonomy we had, there is only unique 3, 0 holomorphic form, right? So
if it is an element of a 2, 1 cohomology, like only condition is that del bar on chi should be 0.
yes,
But here it is a stronger condition, like why it is an element of
it is not stronger in the sense because this is a top form, top 3, 0 form, so del of that form is automatically 0. I mean, it was just a way of saying that it has to belong into 2, 1 form, but that is obvious from when you consider this Ricci flatness condition. I was trying to argue other way around. So if you have d of chi equal to 0, then this variation will satisfy the Ricci flatness condition. Okay? So I am taking an example of T2, and the space of torus is parameterized by this. This is imaginary of Z, and this is we kind of identified these two sides, and this point is kind of tau. Now the coordinate Z on torus is kind of parameterized by x plus tau y. Okay. Now we have only 1, 1 holomorphic form here. So the only possible 1, 1 holomorphic form is some alpha times dz, and that is basically when we write in terms of the coordinates x and y, so it will be dx plus dy, not 1, 1, sorry, 1, 0. Now to get the complex structure moduli of the torus, what we do is kind of integrate it on the one cycles. So if you remember,
Alpha tau dy.
sorry,
So what is, so when it is written in terms of x and y,
Z is, oh yeah, this is alpha tau, not D. Okay, so if you remember, I expanded both scalar moduli and complex structure moduli in terms of some 2, 1 forms and 1, 1 forms. So to get this, what we'll do is kind of integrate on the basis. So this will kind of give a number or something, and then we'll have this t's. So in case of the complex structure, what we define, what we call is a period vector, where the components of it are like pi 1, and that is given by integrating this omega over this y equal to constant cycle, which is basically alpha, and pi 2, which will be x equal to constant cycle. In that picture it is like that, which will be alpha times tau. So these cycles are basically kind of on torus. One will be this and the other one will be this. Okay. Now these two are not independent, because we know in case of torus only independent parameter is tau. So the complex structure moduli of T2 is basically given by the ratio of these two period vectors, which is equal to tau, where alpha is some arbitrary normalization we are choosing here. And similarly, we can have scalar moduli. So we wrote omega as T tilde alpha times some B alpha. And in this case, since we have only one kind of two form, so B alpha is just dx wedge dy, because if you remember omega was our 1,1 form, and that is basically in this case dz bar, and when you write that, the basis of these are basically dx wedge dy. So omega is now this T tilde, because alpha is just 1 here, dx wedge dy, and we know that we can write this omega in terms of the metric. So let's say I define a metric Gij bar dz bar j bar, and when I express this z and z bar in terms of x and y, what I will get is this gzz bar tau minus tau bar. Now comparing these two, and then there will be dx wedge dy. Comparing these two, what we have is the scalar moduli for T2, which is T given in terms of this component of metric, and tau and tau bar. Is that okay? Now we can generalize this example to some n-dimensional compact scalar manifold.
One second.
Yes.
Just to understand, why did you choose alpha to be only constant? Why can't it be some function of z? So there, when you said that you wanted a 1,0 form,
Yes.
I can have a, you've chosen some exact form, right?
Yeah, but that, okay.
All I need is something close.
Yeah. Okay.
So then, if alpha was not a constant, this pi1 integral may not
Be a complicated function of yeah, that is possible. You can do, it's just a simple example.
Okay.
But the fact that these two are kind of not independent, you'll have only one of them acting as the complex structure moduli.
I see. So even if, let's say, I choose some other complicated alpha,
Yes.
if some of the answer will still be
just one complex structure moduli, which will look little bit different than usually what we see in case of. So we will see in general example that is the case. So we have kind of pi vector.
Can you also explain this pattern?
So this is just to, okay. So to get these scalar moduli, we kind of expanded our 1,1 form in terms of this 1,1 harmonic basis times this real term, which was our moduli. So in case of torus, we have only this this harmonic form. So what you have is omega is just t tilde times this basis term, and then we defined omega to we said that we can write omega in terms of this gij dz bar. Okay, so in this case just zz bar, and dz bar I want to kind of replace in terms of x and y to see what is the scalar moduli look like in case of torus. And when you compare these two, our t tilde will look like something this. Okay.
So the odd number of the top scalar form, the omega to the n, is also always 1, right?
Sorry. Yes.
Correct, that will also be just 1.
So we can generalize this example to kind of, to get more general form of these moduli. So in general, omega, which we already saw, can be written as some t tilde alpha b alpha. And in case of Calabi-Yau threefold, we can define the volume. So volume can be defined as 1/6 integration over this whole manifold omega wedge, omega wedge, omega. If you remember, for n dimensional Calabi-Yau, this n times wedge product of omega was kind of giving us the volume element. And if I replace this omega in terms of the what we have written above, which is the scalar moduli and the basis of that 1,1 form, what it will be is b alpha wedge b beta and b gamma, and we have kind of a expression So why I am doing this is usually what we have is the volume, okay, and when we have the volume, I will get the different moduli which are coming from scalar moduli. So to do that, we need these intersection number. These are called the intersection numbers, and once you have that, you can kind of see how many number of scalar moduli are there in a given Calabi-Yau, because H1,1 can be anything. We have not fixed it using the properties of Calabi-Yau. So depending on the example, it can be anything. Now, similar to the torus case, we can also have our general complex structure moduli, which are given by this ZA integrated over some cycle A, and then 3,0 holomorphic form, which was just 1,0 in case of torus, and these GB integrated over this omega. Now the period complete vector, we had there only two components, pi1 and pi2, and those were not independent. So there will be a similar case here. So we will have this Z1, H2,1, and this G1 and G2,1, but these will be kind of function of this Z itself, some complicated functions. And to understand what these cycles are, so in case of torus, I can give an example. So we have these cycles and then these cycles. So I forgot. So this kind of can be B1 and B2, and these one can be A2 and A1. Okay, so now we have kind of parameterized and saw how we can get the moduli fields coming from a given example or given Calabi-Yau manifold. Now we need to see how we can, stabilize them to either have a mass or some vacuum expectation value. Around that we can expand our effective field theory.
Can I ask a question? So when we did the, one of the conditions that you had was that the Ricci tensor of the x6 was 0.
Yes.
And if I compactify on positive genus, then Ricci is always positive. Or like there should be some genus dependent such statement, right? Like, is it true that for many genii you can get Ricci flat? Like in
Yes.
2D, such sphere is never Ricci flat, right? But torus is Ricci flat.
I think Tn is also
Ricci flat.
Ricci flat, yes.
Irrespective of number of genus.
I think so. I mean, I don't know if there is some. I think so, yes.
So only genus 0 is something anomalous.
Yes. We have toroidal compactification of 10D theory to get some, heterotic kind of string.
And they are all Ricci flat.
Yes. Sorry, delta. Yes. J bar, yes. It's the complex conjugate of that. So you take only one to kind of parameterize. Now we are kind of done with the moduli space of Calabi-Yau. So I'll talk about superstring little bit. So I will only talk about what we'll need, not everything. So, but I'll try to give a picture of how we are proceeding. So the action can be written as d2 sigma, and the usual thing we have for our bosonic string, plus, or in this case minus, a term for fermionic string. And after kind of imposing gauge conditions and quantizing, what we'll have is S given in some SB times SF, and where I'll just write the fermionic part. So SF is I by pi d square sigma psi minus del plus psi minus plus psi plus del minus psi plus. Okay. So since all the physical observables will be given in terms of this bilinear functions of this size, so the sign of this size will not be detectable. So we can have like two kind of boundary condition on these fermionic fields, and that is basically what defines our different sectors. So one condition is
This plus minus are light cone quantity?
yes. So plus minus are, we are doing the light cone quantization. So these are let me just write both psi. So psi is given as psi minus and psi plus. These are our left movers. And these are right
But in
movers.
a sense, did you already start from something like a SB plus ASIC, right?
Yes.
You said that after some gauge fixing up.
No. So after gauge fixing and quantizing, we have the in the form of the SF will be like this, and so it's always SB plus SF. Sorry if I stated it wrong. So we have two conditions, which is one is called Raymond boundary condition, where psi of sigma plus pi can be, is equal to psi sigma, and other is Neveu-Schwarz condition. In short form, I'll write just NS. Sigma plus pi will be minus of psi sigma. Now, imposing these conditions on the left movers and right movers, we'll have kind of different combinations of these. So I can write maybe here only. So we can have the psi plus to have the Raymond condition. So it's psi plus sigma, and we can have the psi minus also to satisfy same thing. And this is what is called RR sector. And we can have the other combination as well, which is sigma plus pi equal to, let's say, plus of sigma and sigma minus. So this is, let me know if it is visible or not. So this is RNS type boundary condition, and similarly we can have two more, which is NS and R and NS NS kind of boundary condition.
Just to understand the boundary condition, that is tau sigma and it is with periodicity in sigma, right?
Yes,
The d2 sigma is tau sigma.
yes, d2 sigma is tau, d tau d sigma. Yeah, then you have this periodicity condition. Now, what is the kind of we call mass formula for Neveu-Schwarz sector is given by this. So alpha prime m square. Have I written alpha prime somewhere? Maybe this should be, I don't know. Okay, let's. And going from 1 to infinity, alpha I minus 1, alpha I n. These are the modes for the bosonic fields. And then we have for the fermionic fields, these B minus Ri, B Ri minus half. Okay. Now the ground state Okay. Yes.
In our index sector, we have minus psi plus sigma there.
Sorry, I mean for RR sector, we both had left moving and right moving components to have plus signs when the periodicity. For RNS, the plus one is come with plus sign, and the left moving will come with a minus sign. So let me just write, maybe it will be clear. Sorry?
Are you just writing the components of the MS boundary condition there?
Yes, I mean for the components of this full, spinner, which are in left moving and right moving, so there will be different kind of boundary condition we can impose, because the observables will always come in either psi minus minus kind of thing or psi plus plus kind of thing. So if you kind of flip sign of one, either psi minus or psi plus, will not be able to detect that. Does that?
Maybe that equation when you write Ramon boundary condition Nebuchadnezzar, that psi is any subscript psi alpha equals psi alpha. Is that what you?
Oh, right. Yes. Sorry, yeah. I should have written it like this. So just some arbitrary spinner, if that satisfied that condition, it was called like Raymond boundary condition. But in this case, we need to impose it on both plus and minus.
Sorry, this is not really good. The psi plus always goes to psi plus, even in the Nebuchadnezzar sector.
No, that is after we get rid of tachyons, right? No. No, the fermions can go, right? Is that okay? Okay. So the ground state of this NS sector will have mass which is negative, so alpha prime m square is equal to minus half, because for the ground state these and these will kind of annihilate it. So what we are left with just alpha prime m square equal to minus half, and this is what we call the tachyon. So it is the tachyon. And also there is one more problem, is that with a similar mass, because the ground state is a bosonic state, we don't have any fermion in the theory, so we don't have supersymmetry. So first problem is this, and second problem is that we don't, the kind of SUSY is broken. We started with a supersymmetric action, but the ground state is such that it is broken. Okay, so after kind of expanding the stress energy tensor in terms of the Virasoro operators, what we get is a level matching condition, and from there you get this mass condition.
P square equal to minus m square.
Huh?
P square equal to minus m square.
P square equal to minus m square. Yes. I haven't defined any metric here, but okay. So yeah, so the ground state of the NS sector is a bosonic state, right? And it has a mass, which is some mass, but we don't have a similar fermion with same mass, right? We don't have a fermion with a minus 1/2 over alpha prime square mass. So in that sense, supersymmetry is kind of broken. Now to remove this problem, what we do is we truncate our spectrum. Sorry, I keep taking this. And that is we do by.
So this half comes from the bosonic sector, right? This minus half.
when we kind of cancel the anomaly term, the A is said to be half.
I'm trying to see why it is there is a term for the bosonic but not the fermionic.
I'm not writing for the fermionic term, right?
No, I'm saying that this minus half term is a mass spectrum.
Yes.
This is coming from bosonic part or fermionic part, or where is it exactly coming from?
It is coming
It's a both. Because you see, these B's are kind of modes for the fermionic fields and alphas are for the bosonic fields. So mass is coming from both.
No, that is fine. I'm saying it's minus half.
So it is for the ground state, that is bosonic. Okay. So to remove this inconsistency, what we do is truncate the spectrum, and that we do by taking a projection. So we take a projection which is called GSO projection. I don't remember the names coming in this, so if anyone knows, maybe they can tell. Olive, I remember. It is fine, we can just, some people, GS and O. So for NS sector, it is defined as NS minus 1. I mean, the operator for this projection is defined as this, where F is kind of sum of these fermionic modes. And for the R sector, it is defined as, I mean, in our case, I can write it as 1 plus lambda gamma 11. Now, because for the ground state, there is no fermions there, so F is 0 basically, because the ground state is bosonic. So under the GSO projection, what we have is the ground state of NS sector have a minus sign coming in, and we kind of leave that ground state. So to get a consistent theory, what we do is we take only the plus, projection for NS sector and both plus and minus projection for R sector. So after projection, we have only NS plus and both R plus and R minus, because the ground state of R sector didn't have any problem as the ground state of the NS sector, and the ground state is
Can you explain the GSO projection once more? What exactly?
So it is kind of designed to get rid of this tachyon here. So for NS sector, the tachyon is coming from the ground state, which is basically the F is equal to 0 for that. So for NS sector, we have defined it to be minus 1 to the power F plus 1, where F is kind of fermion number. And for R sector, it's half plus gamma 11. Gamma 11 is the gamma 1, gamma 10. Yeah. Yeah, Clifford. Kind of like gamma 5 in 4D. And yeah, so after taking this projection.
This is the problem of generic any supersymmetric theory. The ground state will always break in a supersymmetry, because if there is nothing or there is particle after particle theory.
But it doesn't have mass, right? The ground state doesn't have mass in generic theories, right? I think, I don't know, but the main problem is tachyon here. If like it's negative.
I'm just saying that suppose we start with supersymmetric theory, the ground state is always supposed to, the vacuum is always supposed to break.
No.
No.
If you are at 0, then it will not, right?
Yeah, otherwise it's supersymmetry breaking. You can have, if you take, let's say, simple supersymmetry, quantum mechanics or something, H is q plus q bar square, right? And H will commute with q. So if vacuum has 0 energy, then the vacuum is invariant under supersymmetry.
I'm just trying to make it again. Either I can have nothing or at most particle antiparticle phase.
So nothing doesn't break Susi, right?
But we can have like fermion kind of. Okay, no, that. Yeah, yeah. Yes.
It will transform under. Won't be defining.
No, I mean, I take the supercharges act on vacuum is 0 for me. So that means, how do I say the vacuum is fermionic, bosonic, or anything like that?
From Lorentz, if you have additional chemistry, right?
Even if I act Lorentz on vacuum, if it's 0 for me.
No, because you still have to give you like premium.
Right.
And the premium that should be 0.
Yes.
And now if I say that.
So then how do I say vacuum is fermionic or boson vacuum? It is vacuum in that kind of example, right? Supersymmetry is invariant, vacuum is the vacuum.
It's not like the Whitman index will vanish, right? It will be 1 for the vacuum, and every excited state it will vanish. So Whitman index will be 1. Right?
Even for when you analyze vacuum.
Yeah, I mean supersymmetry would like it's like a trivial index, right? But it's not V. It will be 1.
Oh, okay, right. Because it's a power of right. That's how the nature of its definition is defined. Like if the Witten index is 1, then it's bosonic. If it's
The supersymmetry is trivial,
right.
I think so. We are talking about vacuum state, right? So when it is massless, I don't know if we want to correspond it to some kind of field or particle, but here it is kind of massive, so we are kind of corresponding it to some particle. I don't know the exact. For you.
We have, for instance, a similar formula for the RAM also.
Yes, but there we don't have a, yeah.
The random situation the vacuum is degenerate, then it's
Okay. Yeah. So after projecting out this tachyon, what we have is this NS plus under GSO projection and R plus and R minus. Now in 10D we have 2 to the power d by 2, which is in 10D 32 complex components of a spinner. So in in 10D we can impose the condition, which is what we call Majorana condition and Weyl condition on this spinner, and that will reduce the number of component. So this will reduce by 2 and this will also reduce by 2. So it will have like 8 complex or 16 real components. Okay. Now, is it? Okay. So, now after imposing Dirac equation on this 16 component, 16 real component spinner on shell, we will have 8 component kind of spinner, and again on shell we will have 8 component vector field. because the vector fields were kind of given by x mu and the spinner was given by psi. So for on shell condition, what we have is kind of we fix the x plus minus, which is x plus is given by I think x0 plus I times x10 and x minus is similar with minus sign. And when you impose the equation of motion on these fields, what you have is kind of x plus is also fixed and x minus is also fixed in terms of the rest of these xi's, and we are left only with the 8 kind of independent components of the vector field. So it is to motivate that what we have is a representation of SO8 in 10D. So on shell we have 8 vector and 8 spinner transforming under SO8. Now in type 2B string theory, what will be the field components? So let me just write, we will have 4 different sectors, which is ns plus with ns plus, and then ns plus with r plus, and the other way around, and then we'll have r plus with r plus. So the difference between type 2A and type 2B is, in type 2B we kind of impose a specific chirality on the spinner, and in type 2, did I say type 2A or B? Okay. Okay, so let me just write. So in type 2A we can have both r plus and r minus for spinner, and type 2B we have only r plus. So that is why this. And under SO8 this will be 8 vector cross 8 vector, and that will be equivalent to 1 plus 28 plus 35, which will be given as a 0 form field, which is a scalar that we call dilaton, and a 2 form field antisymmetric by definition. And then we'll have the symmetric metric, and you can count the components, it will match. And in this case we have this 8 vector cross 8 spinner, that will give me 8 prime plus 56. It will correspond to a spinner and a gravitini. And similar for this case as well. And when we take r plus, it will be 8 cross 8, and that is again the same thing, 1 plus 28 plus 35, and it will give me a 0 form antisymmetric and 2 form, this I call C0, and a 4 form. Can I just take like this one page of my notes? I don't know how much time it will take, so I'm just telling that I'll have this one page. Just let me just give a, the components of, the field content. So tomorrow we can start by writing the action for type 2B and see how we stabilize this moduli. Okay. So what we have from there is a GMN, which is 10D metric, then B2, which is a kind of a background field, so 2 form field, and then we have phi, which is our dilaton, and I'm just writing the bosonic component, that is what we will need. So the bosonic fields, and then we have this C0, C2 and C4, which we call potentials, because corresponding to them we will define a field strength. So D of C2p plus 1, because it looks like that only, so it will be F2p, will be F2p plus 1. And then for B2 as well we'll have a field strength, so dB2 is what we call H3. So you see we have like a 3 form field strength. So just cheating we can do here is that up to this level we can only stabilize the H2, 1 moduli, because any P form can be only integrated over a P dimensional manifold, and only we have 3 field strength here for like C2. We don't have a 2 field strength which is kind of going to stabilize H1, 1. So we at this point we can see that in type 2b we can stabilize only the 2, 1 moduli, which are the complex structure moduli, but we will see that is also not possible without having something called D branes. Okay, so I'll just give an analogy between electromagnetic fields and type 2b fields to understand a little bit about D brane, because we will not be talking much about it. So an analogy between we have our potentials. In case of, we have here A mu, which is nothing but a one form potential, and in this case we have C2P, and then we have field strength, which is basically this D of A1, and maybe I should write it like F mu nu in this case, which is nothing but D of this A1, and similarly we have here D of 2P, which are F2P plus 1, and then we have the action, which is D4x F mu nu F mu nu, and in terms of these forms it will be F2 wedge star F2, and using this analogy the potential here will be something like that. So minus square root G hot star F squared 2P plus 1. So it is equivalent to that. Now we have something we call source, which is in this case a charge, and that I am going to call a D0 brane, and corresponding to that we can have 2P minus 1 branes here, and this is something which is local thing. So D branes are kind of local objects in type 2b, and the action for source is Q D. So this is the word line of the charged particle, this psi A mu, or in this notation we can write 1 over this C, and we can have flux once we have a source, and that is basically integrated over the surface through which we measure the flux F mu nu, or in this case just some two-dimensional surface. Okay, so the source for for action for the d branes will look like something similar to that. This mu c to p, this curly w, where curly w is the walled volume of the d branes, and we can have similarly flux for these local sources. Okay. Now we know in case of like electromagnetic theory that if we kind of integrate this flux over some closed surface, then it gives us 0, right, unless we have a monopole, right. So same analogy is there. So monopole is something non-trivial in electromagnetic theory. Same analogy will take that the fluxes which we want are usually 0 unless we have something called non-trivial, I mean d branes. Okay. So I'll stop here only. That I'll show tomorrow that why the fluxes are 0 in type 2b unless we have some local sources which are in our case will be d branes. Okay. Any questions?